Okay, today we're going to talk about the mechanical design to project 2. It's our power transmission system design. I'm Joseph Villamor. This is Narine, Kelvin, Harrylall, and
I'm Arvind, Parsan.
Our basic problem statement is what we got for our individual transmission system is our input and output shafts need to be parallel and be aligned. We also have our application is only for high precision. We add indoor light shots and operate at room temperature. And then we also had 5 horsepower to transmit in the input. Our ends were 950 RPMs, and our output was 100 RPMs. Our inner and outer diameter direction had to be opposite. And that was our last basic step for our analysis that we need to start with.
Okay, so I'm going to give an introduction. The first thing would be, what is a speed reducer? A speed reducer reduces the speed between an input and output shaft. For our instance, we have an input of 950 RPM and an output of 100 RPM. So that means that there's a 9.5 reduction, a 9.5 ratio reduction in speed. So how does it work? A gear train speed reducer works by mating 2 gears of different sizes. If a gear of 1 centimeter mates with a gear of 2 centimeters, the gear that's 1 centimeter is going to have to spin twice as fast to keep up with the gear that's 2 centimeters. So why is it needed? It is needed for an application that needs a lower RPM but higher torque, because torque is inversely proportional to the velocity ratio.
Basic disadvantages of the speed reducer is basically, obviously, the loss of speed, and then also is the weight issues. When you add in all the gears, it actually gives you a lot more weight, and that's kind of a disadvantage for most of the transmission systems.
Some of the advantages of a speed reducer involve managing speed. You're able to bring the output speed to a very manageable speed based on the gear ratio that you have. Also, motors do not have to work as hard. There's also the torque, as I said previously, is inversely proportional to the amount of reduction in the gearbox. This means that if there's a 4-to-1 gearbox ratio, then the output speed will be 1/4, but the torque will be 4 times higher. So this is our first conceptual design, which consists of 9 gears, an idler gear here which changes the input and output direction. We decided not to use this model because it was overly complicated for the purpose that we needed. Thus, we created a much simpler idea as seen here.
And here we see the proposed design. As Kelvin listed, we went from the 9-gear model to the 5-gear model, both to optimize cost, efficiency, and compactness. Here is our 5-gear model with 5 bearings on 4 shafts. As you can see, gear 1 drives gear 2. Gear 2 functions as the idler to basically change the input that is clockwise into an output which is counterclockwise. Gear 3 is much larger than gear 1 and 2, which contributes to the reduction. On shaft 2 is also bonded gear 4, which drives the output of gear 5. As you see, gear 5 has the highest pitch diameter, drives the output shaft. And an important thing to note is that we were able to meet our specification of having the input and output shafts on the same axis. Previous slide, please. And here we see more views, the isometric view, the side views. Next slide. In bearing selection, basically, after we selected gears in the Boston catalog, we then went through a force analysis. We found the tangential force, which we then divided into axial and radial forces. Based upon those forces and equation for the C0 value in the textbook, we were able to define the C0 value and then use that value coupled with the pitch diameter of the gears to select a bearing that would not exceed the pitch diameter of the gears, but at the same time would offer the ability to withstand the radial and axial loads as combined in the C0 value. So we went to the Timken ball bearing catalog. We used ball bearings because of their availability, their affordability, and the fact that because we used spur gears, there was no axial there was no thrust force. So there was not the need for a tapered bearing. So we went with a ball bearing, and that concludes the bearing selection. Next slide, please. As I previously stated, the torque was determined, the tangential force was determined, and we determined specifically which bearing we needed. Next slide, please. In our shaft design, based upon the bore diameter of the bearings, we then chose the diameter of the shaft on steel alloy 4140 because of its corrosion resistance, its manufacturability, its machinability, and its wear resistance. We then examined in computational software both deflection and strain under the appropriate forces, and the deflection and strain reported was at a negligible value, therefore indicating that the system is structurally intact for shafts. The entire assembly was put together in 3D software. We used shaft collars to mount the second shaft, and we also made the shafts very short in length to minimize moments. As you can see, our design only costs about $1,300 to manufacture. The majority of that cost is machining and welding. Basic maintenance includes lubrication, visual inspection, and inspection through a caliper. Our application is a high torque industrial motor with low RPM for cutting through abrasive material. As you can see here, there is a picture of an industrial circular saw. Next slide. In conclusion, this was a very helpful project. We were able to practice our solid animation skills, our CAD. We were able to learn how to read industrial catalogs and go through the complete gearbox design process. Next slide. As you can see here, here's our application with a circular saw wafer fixed onto the output shaft. Next slide. And as you can see here, this is our animation moving. Thank you very much.